Hello and welcome. Today we're going to talk about more optimization problem examples. I'm going to go over two with you guys, and the examples are going to highlight some of the kind of maybe less intuitive aspects of how optimization works. So the first, and we're going to make these ones a bit more authentic and in terms of like situations where there's certainly more of a business sense to the issue. So the first we're going to talk about is basically maximizing area again. Maximizing area of an enclosed space. In this case, it's going to be a rectangle again. Okay, but the problem is going to be involving fencing. Okay, so the fencing, we're going to have 2,000 meters of material. All right, but in addition to that, one of the boundaries is going to be a river. Okay, so the situation we have here is essentially we have, I'll draw that a little bit more vertical, like that. We have a enclosure that on three sides is going to be fence, but to keep our animals in the pen on the other side, we're going to have a river right here. And for that side, we don't need to have any fencing on it at all. The river is a natural boundary to keep our cows in or whatever. All right, so the idea here is, again, we have to identify variables. In this case, we have x, which is going to be that broad side there. And of course, we also have y. We have y on that other side too. And we have to choose what dimensions of fence. And let's say that we have enough riverfront property here that we're never going to run out of space. We just want to maximize the area. And of course, the area inside is going to be equal to x times y, just like we did in the previous video. So of course, our objective function is going to be a of x comma y is equal to x times y. And our budget, or our constraint, that equation is going to be that we have 2,000 meters to work with, in which case we need, of course, 2y, but only 1x, because of course the river is some free fencing essentially that we don't need to account for. So this becomes our constraint equation. So taken together, this is all the ingredients we need now to maximize the area. So the first thing, of course, to do is solve for y in terms of x. So we're going to have 2,000 minus x is equal to 2y. I can now solve for y, and that's going to be 1,000. We're going to divide by 2 over x, or minus x over 2. Okay, there is our equation. There is our function of x. Y is a function of x. And now, of course, we're going to plug into the objective. Okay, and the objective function is going to be area of x of y of x is equal to x times, and now instead of putting y there, we're going to put 1,000 minus x over 2. All right, I can simplify this a little bit, or at least multiply through to get that. All right, the next thing we need to do is, of course, maximize the area, and we do so by finding its zero derivative. So we take the derivative of the area function, and we're going to get 1,000 minus x. We're going to set that equal to 0, and it's pretty obvious here that x is going to equal 1,000. That's the only number, the only choice for x that's going to give us a critical value. So we'll call that our x star. Of course, y then can be determined simply enough We know we have 2,000 meters of fencing left over, 1,000 meters of fencing left over, and so y better be half that, so it's going to be 1,000 minus 1,000 over 2, otherwise known as 500. Okay. So what's interesting about this, so interestingly, of course, when we maximize the area of a rectangle with 4 sides, like we did in the previous video, we got a square. However, here, with only 3 sides, okay, we got one side for free because of that river. What we got is actually a rectangle. A rectangle. In fact, it had a specific aspect ratio. We had 1,000 on one side. We had 500 on the height. So this had a 2-to-1 aspect ratio. And you can expect from any size of enclosure, whatever budget you're given, half of it's going to go to the broad side, and the other half will be split amongst the height of the fence. Every time that will be what happens. So you're always going to get that 2-to-1 aspect ratio. So here, a rectangle, which is a non-square, results. So that's interesting. All right, let's see if we can come up with another similar analogous problem now. And we're going to do, again, a cylinder. So what we're going to do now is going to do a minimization problem. Minimization of surface area. Given a fixed volume. Okay, in this case, the object, we're going to do a cylinder again. So in this case, we're going to say it's going to have a fixed volume, V equal to 1 liter. Okay? All right, so what we want to find now is, of course, we're going to minimize the area. So this is going to be our objective function. So V now is our constraint equation. And we know that every cylinder, let's draw a better cylinder here. Every cylinder has 2 parameters that define the cylinder. That's going to be the radius as well as the height. All right, so V of R and H, we know that's going to be equal to 1. So now this is our constraint. Okay, and our objective function, that's going to be now the area, and that's going to be a function of R and H, which is going to be equal to those 2 end caps. So we're going to have 2 times pi r squared plus the perimeter 2 pi r times h. Okay? And the volume, r comma h, is going to be, again, it's going to be pi r squared, that's the area of the disk end cap, multiplied by the height. Okay, we're going to set that equal to 1. All right, so as with all of these problems, we want to solve, here we're going to solve for h in terms of r, so we're going to find the function, and that should be pretty easy. From this equation, we can see pretty easy that h is going to be equal to 1 liter over pi r squared. So that's our function for h. And now we're going to plug it in here and get a of r of h of r comma h of r. We're going to get 2 pi r squared plus 2 pi r times 1 over pi r squared. We can simplify this up. We're going to get 2 pi r squared. The pi's cancel there. One of the r's cancels there. And we're left with plus 2 over r. All right, so the next stage is to take the derivative of the area with respect to the radius. Now we're going to get 4 pi r, and then we're going to get minus 2 over r squared for the derivative of the 1 over r term, and then we're going to set it equal to 0. Solving for r now, we have to find that critical value. We're going to multiply everything by r squared. We're going to end up with 4 pi r cubed minus 2 is equal to 0. We can, and then what we'll do is say that r cubed is equal to 2 over 4 pi, otherwise known as, is known as 1 over 2 pi. And then we can get r is equal to the cube root of 1 over 2 pi. Okay, great. We have that value there. That's looking pretty good. The next thing we want to do then is find out what that height is. The height, of course, we just have to plug back in what the height is. And we see right there it's going to be pi over, or 1 over pi multiplied by, now it's going to be 1 over 2 pi to the 2/3 power.